Welcome to session 3 of unit 2, amount of substance and the mole. This very session is looking at quantity of solute in solution. In other words, concentration of solution. This session has the following objectives. We'll define a solution, define amount concentration, we'll define mass concentration, we'll define molality, we'll explain mole fraction, we'll solve problems on the various types of concentration. Our first objective: solute, solvent, solution, and concentration. We are dealing with solutions, and so these are terms that we should know before we continue. And so when you take a solution, there are two basic components. You have the solute and the solvent. They come together to form the solution. The solute is the substance that dissolves in the solvent, usually in the small quantity, whilst the solvent is a substance that does or that dissolves the solute. So it does the dissolving or dissolves the solute. It is usually a liquid, or in a case where it is hard to determine which one is the solute and which one is the solvent is usually in a larger quantity as compared to the solute. So we put solute in a solvent to form a solution. If that's the case, then what is the solution? It is a homogeneous or uniform mixture of solute and solvent. So now that we know we have put solute in a solvent to have our solution, then we can talk about the quantity of solute in the solution, and that is the concentration. Quantity of solute in a solvent or in a solution gives us our concentration. Now with the concentration, we have, or due to the various ways in which we can express the solute, we can talk about different types of concentration. For example, we have amount concentration, that is molarity. We have mass concentration, we have molality, we have mole fraction, and then we have concentrations expressed in terms of percentages, etc. There are a number of them. Now, this course is going to look at amount concentration, which is molarity, mass concentration, molality, and then the mole fraction. So let's start with the amount concentration. With the amount concentration, we are expressing the mass in terms of moles, and then we are dissolving in 1 dm cube of a solution. Now this means that whenever we are talking about amount concentration, we want to see moles, we want to see cubic decimeters. So if your volume is in cubic centimeters, then you have to convert it into cubic decimeters. And if the mass or if the solute is expressed in grams or any other unit, you would have to convert it into moles. Then you can find your amount concentration. So given that amount concentration is the number of moles dissolved in 1 dm, then we would have the unit as moles in dm cube, moles in 1 dm cubed. It is also expressed as moles per liter or moles in 1 liter, or it is also expressed as molar, that is capital M. Why these different expressions, the dm cube and the liter? It's because we can be converting our volumes. For example, 1000 cubic centimeters is equivalent to 1000 milliliters, which is equivalent to 1 cubic decimeters, and then which is also equivalent to 1 liter. So if 1 dm cubed is equivalent to 1 liter, then we can express concentration also in terms of moles per liter. So whenever you are given a problem and the volume is not in cubic decimeters, is not in liters, kindly convert into cubic decimeters or liter. So from the definition, we can say that amount concentration. Now you should also note that amount concentration is also referred to as molarity, molarity, and it is expressed as amount in moles over volume in cubic decimeters. If you remember when we were treating number of moles or the mole, we said that mole is expressed as mass over molar mass. So we can substitute mass over molar mass in place of the amount, which is N, and that gives us concentration to be mass over molar mass times volume. You are going to choose between concentration being equal to number of moles over volume and concentration being equal to mass over molar mass times volume, depending on the kind of question you have been given and how you want to approach it. So let's take an example. We are to calculate the concentration in moles per liter of 8 grams of sodium hydroxide dissolved in 500 cubic centimeters of solution. We have been given the atomic masses of the sodium, the oxygen, and the hydrogen. So let's look at how we would approach this problem. We are going to need our molar mass. For whichever formula we choose, we will need our molar mass because we've not been given moles. So from the atomic masses, we have the molar mass of sodium hydroxide to be 40 grams per mole. Next is to check the volume. Is it in cubic decimeters? If it is, fine, we use it straight away. If it is not, then we would have to do our conversion, where we divide the 500 cubic centimeters given by 1000 to give us 0.5 cubic decimeters. In other words, if 1000 cubic centimeters is equal to 1 cubic decimeter, then 500 is equal to what? You cross multiply and you have this answer. So knowing this and the question or data from the question, we having the mass as 8 grams, we could have chosen the other relation where concentration, amount concentration C is equal to N over V. In that case, we would have calculated for the N, the number of moles separately, and then bring it here. We would have calculated for it separately and then bring it in the formula. But in this case, we just want to do everything straight away. So we choose this relation where we have our mass, we have our molar mass, we have volume. So the mass and the molar mass account for the number of moles. The rest is to put in our values, and our answer is 0.4 moles per decimeters cubed. Next is to look at mass concentration. So this time round, we are not expressing absolute in moles, but we are expressing it in terms of grams. So there's a mass of substance in grams dissolved in 1 dm cube of a solution. By such definition, we can say mass concentration is equal to mass over volume. Take note of this volume. This volume is in cubic decimeters. If we leave it in cubic centimeters, then we are talking of density. So if we want the mass concentration, then we want the volume in cubic decimeters. Mass concentration is usually represented with a symbol rho. So we can relate mass concentration to amount concentration, which is molarity, and molar mass. In a case where using mass over volume in dm cube is not applicable, we can go for this relation, which is molarity by molar mass. In all, you should check to be sure that you have the unit. What is the unit? The unit is grams per cubic decimeters. So we have rho being equal to capital C times capital M. We'll be using it a lot. Now, one thing you should note whenever you are doing the writing is the unit. We have said that mass concentration has the unit grams per cubic decimeters. So when you do any calculation that you are getting a different unit, then check your process well. You might have done something wrong. There is a problem here for us to try our hands on, is to look for the concentration or the mass concentration of 0.75 molar sodium carbonate solution. If you remember, we said amount concentration can also be expressed in terms of molar or in molar. We have our relative atomic masses given. So we proceed to look at our answer. With the answer, we need to find the molar mass of the sodium carbonate. And just like we have been doing, we do same here, and we have 106 grams per mole. Then we can go for our relation amount mass concentration is equal to amount concentration times molar mass, and that gives us 79.5 grams per decimeters cube. Given that you don't even know the formula, yet you want to find the answer, then you should remember the unit of mass concentration. Once you remember the units, write down your parameters. You have been given amount concentration, which is mole per cubic decimeters. You have been given mass concentration. The question you need to ask yourself is, how do I manipulate this amount concentration and molar mass such that my unit is going to be grams per cubic decimeters? When you try to find answer to this question, you arrive at the answer. So you know that because the mole is positive, the decimeter cubed is negative, and on the other hand, the gram is positive, the mole is negative. You know that when you multiply them, then the mole will cancel the per mole, and then you will now be left with gram, which is positive, as against dm cubed, which is negative. So that will give you the relation, and you would arrive at a beautiful answer. The next to look at is molarity. This is molarity, not molarity. And molarity, we are expressing the mass in moles, but then we are dissolving it in 1 kilogram of a solvent. This time round, not in decimeters cubed, but then in kilograms. So in other words, we are weighing the solvent rather than measuring the volume, or we are talking about mass of the solvent rather than volume of the solvent. And from the unit we have there, which is mole per kilograms, it means we are going to divide amount of substance by the mass of the solvent. So we have a problem here where we are to find the molarity of 8 grams of sodium hydroxide dissolved in 400 grams of water. Remember, because our unit is kilogram, the grams there we have to express it in terms of kilogram, and then that is the grams of the water we have to express it in kilograms, and then the grams of the sodium hydroxide we have to express in terms of moles. But the relation is given as molarity being equal to moles of solute N over mass of solvent in kilograms. Now we have our mass, we can find the molar mass of the sodium hydroxide. We do that in order to find the number of moles, and we have our number of moles to be 0.2. So knowing the number of moles, we just go back to our relation for the molarity, do our substitution. Like I said, we have to convert the mass of the solvent, which is in grams, into kilograms, and that gives us 0.4 kilograms. Then we do our substitution into the molarity relation, and we have 0.5 mole per kilogram. So that is for molarity. Next is mole fraction, and here we are referring to the ratio of the mole of substance to the total number of moles of all components of a solution. So here we'll be dealing with moles. Whatever the question is, we first have to find the moles, and then we can proceed. It is denoted by capital X, and then we write what the particular species we are looking for as a subscript to the X. So for example, in a solution where we have components A, B, C, and we want to find the mole fraction of, let's say, A, then we know that moles is represented by the letter small n. So small n subscript capital A represent the moles of A, and the mole fraction is given as X of A, and in this case we are going to divide the moles of that particular components by the total number of moles, which is giving us, so with the total number of moles, we are only adding all the moles together. So moles, in this case where we have three components, moles of A plus moles of B plus moles of C. So if we want mole fraction of A, we just divide the moles of A by the total number of moles, and it applies to all the components in the solution. So there is an example here for us to try where we are to find the mole fraction of oxygen, carbon dioxide, and nitrogen. We've been given masses and atomic masses. What do? We have to find the moles, or we have to express these masses in terms of moles for each of the components. Then we can proceed to find our mole ratios. So we have been given atomic masses, we find our molar masses. So molar mass, with the mass we find the moles. So we'll do for all the components to get the moles. Now that we have the moles, we can add the moles together to get our total number of moles, so that if we pick a particular component and we want to find its mole fraction, we just divide its mole by the total number of moles. So for example, with the mole fraction of oxygen gas, we just divide the moles of oxygen by the total number of moles, and that gives us 0.4. So we are ending the session here with questions. Try them, try to solve them, and I hope you enjoyed this session.